This is House Planning Help episode 331. Hi there, I'm Ben Adam Smith, and this is the podcast for you if you're interested in self-build or retrofit. I'm exploring what houses we should be building in the 21st century and trying to break down the major roadblocks that may get in our way. Coming up in this session, my guest is Alan Clarke. We're concluding a mini-series that we're doing examining different professions, people that you might encounter on your self-build or retrofit journey. Today, under the spotlight, a mechanical services engineer. What exactly is that? First, though, I always like to highlight other people doing good work, interesting work, and particularly if it relates to what we're all interested in, which is housing. So Facing Future is a non-profit. They stand for the protection and preservation of life on Earth. They want to raise awareness, change the status quo, and amplify the voices of climate activists. So they do all sorts of content, but they've dedicated an episode of their video discussions that they put online every month to housing. And it's pretty good. In fact, a lot of the stuff, if you listen to our podcast, I think everything in there we have mentioned on a podcast, with the exception of one thing. So let me tell you who's on there, first of all. All of these people have been on the podcast before. Mike Coe, who first built the Cropthorne Autonomous House and then went on to build Portree Passive House. Lloyd Alter, who wrote for Tree Hugger extensively. More recently, he's author of a book that looks into carbon footprints and how we can all take a bit of responsibility ourselves. And Chris Magwood, he's written possibly 8 or 9 books, all focusing on wonderful materials, but not only that, saying that you can have it all. It's about being intentional. And this is the bit that I've never heard before. He's saying he's really excited by what's happening recently, developments with mycelium and how we might be growing our insulation in future. Maybe that's one for Google and possibly one for my ideas list for the podcast. But we'll put a link in the show notes if you want to check that out. Facing Future with their episode on housing. Let's get to our featured interview today. It's with Alan Clarke, who also has been on the podcast before. I've been doing some filming with Alan. He's a mechanical services engineer and is actually, as you'll hear in this, working on training material for another project. But I just thought this was interesting to mention this before we get going, because Alan is very logical, very analytical, common sense, very good at looking at efficiencies and so forth. And I've been out on multiple different shoots over the years and never clocked this one. He said in the middle of our shoot, "I think you're using your eyepiece on the camera the wrong way round." And I took a look at it because, of course, it's designed in a specific way and had to agree with him. So, of course, I changed to my other eye and immediately I couldn't do it because I think I've been doing it for so long. I couldn't make it work the other way round. But it just goes to show it's a bit like Sherlock Holmes, that Sherlock Holmes would pick up on all the clues and things. And I think that's very much what Alan does in the world of mechanical services and just looking for efficiencies. And that's why he's teaching all this stuff these days. So over the last couple of episodes, we've looked at different professionals that you might meet or need for your self-build or retrofit project. And today we're finishing that mini-series by looking at the role of a mechanical services engineer. So we'll explore what that means, what areas they cover, how we might interact with them, and so forth. Firstly, I asked Alan, what is a mechanical services engineer?
Well, in the design of buildings, this will cover the design of the heating system and ventilation system. And it could be, some practices would just do mechanical services design, and then there's also M&E or MEP, which would be mechanical engineering and public health, which would cover all the building services. So as well as the heating and ventilation, it would be the electrical services and the drainage, and of course the plumbing as well.
Is this a discipline within engineering?
Most of the people practicing it professionally would come from an engineering training, yes. And you might be a chartered engineer to do this, yeah.
So when might we look to getting a mechanical services engineer on board?
So there's quite a choice of options with a domestic, house-sized project, particularly on the electrical design, for instance. An electrical installer would be expected to be qualified and understand the regulations and understand how to install a system that is going to be in line with the wiring regulations and building regulations compliant. So you may not particularly need to get anyone else in to look at that. Similarly but differently, there isn't quite the same level of qualification and supervision on ventilation services and heating services. So actually full ventilation systems in houses is a fairly new endeavour, new field. So there are now some qualifications just for installers and so on to work to, but you might also be looking at an engineer to design a whole system for you as well.
What part of the building regulations are we talking about in this mechanical services section?
In England and Wales, this is Part F for ventilation, and basically Part L covers the energy of the house as a whole, so that would cover the heating system. But that would also go on to include the insulation and might include energy modelling of the building as well.
And when we're thinking about houses, we often have an architect on board. Will they sometimes do this in-house?
It's unusual for an architect to go into much detail on the design of these things. I know one who would do a fairly detailed design, one or two, but it's more common for them to basically lay out the regulatory requirements and leave it to suppliers and installers to fill in the detail.
And at what stage will the architect's designs be at before they would hand over to someone like you?
There's a couple of ways of thinking of this. So my particular field is passive house buildings, and we have some requirements that architects new to this might not be really familiar with in terms of integrating a mechanical ventilation system so that it works efficiently, is easy to maintain and so on. So there's some spatial requirements. At REBA Stage 3, pre-planning would be a time to be coming in and actually thinking about where the main items of equipment are going to be located and how the distributions through the building would work. So ductwork is just a lot bigger than pipes and wires, so it's good to have a plan as to how that's going to work, although you wouldn't get into the detailed design at this stage. Now also, if we're doing a passive house, there's another wing to this sort of work, which is doing the energy consultancy and passive house energy modelling with PHPP. These could be two different people, it could be the same person, I could do one or I could do the other. But again, if you're doing something that requires an energy model, you ought to be doing that before you put planning application in, because that might have knock-on effects on the form of the building, window sizes and that kind of thing. That will affect the external appearance.
So when we're looking at ventilation, what sort of things are going to make it a really efficient system?
In terms of the overall system, in terms of energy efficiency, one of the key things is the MVHR unit. Is that actually an efficient piece of kit with good heat recovery efficiency and quiet, efficient fans? However, you can scupper the sort of fan performance by putting in ducts that are too small. Then the fans have to work much harder. You use more energy running them, and you get more noise as the fans work harder as well. So that's kind of lose-lose. So having a good approach to the design of the ductwork is important there to get an efficient system. The other side on the heat loss, something that's not particularly recognised in the normal Part L calculation for building regulations, but is in the passive house analysis, is looking at how long the ducts bringing cold air in and out of the building are and how well insulated they are. If we do the calculations accurately on those, we see that we want to keep those really as short as possible, within 1 or 2 metres length, which has serious implications on where you're going to put the ventilation unit. And then experience has shown for keeping it running optimally, it needs regular filter changes. That's not going to happen if it's in a dark, inaccessible loft. It needs to be somewhere where you can get to it and see what you're doing, and it's safe to access. So there's a whole lot of strategic planning in order to get to the efficient system before you even start installing it.
And then as well, you've got where you're bringing the air into the building. You have to separate the ducts in a certain way. And what are your options there?
Going back to the basic principles of what we're trying to do with a balanced mechanical ventilation system with heat recovery is bring in fresh air and take out stale air, particularly from the smelliest parts of the building, which obviously we don't want to take air from those into the cleaner places where we're spending more time. So we supply fresh air to the bedrooms, living rooms and a study and such like, and we extract air from the wetter places as well, the bathrooms, utility room and kitchen. And the point of the heat recovery system is that we pass that extract air through the MVHR unit, which has got a heat exchanger. That transfers practically all the warmth from that extract air to the incoming air, so that comes in with virtually no heat loss to the building, and you get warm air coming in at room temperature, that is, not any warmer, but that's fine, and that means you don't feel cold drafts. You get a high level of ventilation even through the coldest conditions, and you get a nice fresh indoor climate as a result.
How are you dealing with the ducting then when you are doing your designs? What makes it an efficient design?
There's a couple of things to the ducting. So you'd have your ventilation unit, say in a utility room, that might be an ideal sort of place, and you run ductwork from there to your bedrooms and living rooms. You'd also have ductwork connected from there to the bathroom, kitchen and so on. And you kind of want similar sort of resistance to airflow from all those rooms. So if the ductwork is connected up with what we call a radial system with lots of separate ducts, then that's conceptually quite easy to see that you just run a duct to each room. But if you want more air to go to that room or from that room, you run two ducts. Also, if it's got a long way to go, then the resistance of running down that duct is higher, so you might increase the number of ducts to a distant room just to make it easier to get air from there to the MVHR. The other system we use is what's called a branched system. So you then start with the biggest duct at the MVHR. It goes off to the first room. You tee off there to a terminal there. The duct carries on to another room and it tees off again, and so on. The main duct size reducing as you go along. And in a normal sort of 3-bedroom house, we're probably starting with a duct size of 150 to 160 millimetres, that's 6 inches, and then just dropping down to 100 millimetres or 4 inches to individual rooms. If we're using the radial system with lots of ducts spreading out, they're generally on an outside diameter of 75 or 90 millimetres, which is a bit easier to thread through buildings, but you need more of them.
Does that mean that the radial system is easier for a self-builder to install? Because you need to have a little bit of planning, don't you, if you're using rigid ductwork, etc., threading them through posi joists?
I would say they both need some planning, to be honest. I mean, this is one of the places where actually you can go to a specialist supplier. There's probably half a dozen I would look to who can do a detailed design of a system and supply all their equipment. They could do that in a rigid ductwork system or a radial semi-rigid system. So the semi-rigid stuff comes in a big roll. When we say semi-rigid, it's kind of not a flexible duct in that you can stand on it and squash it. It will maintain its shape, but it is bendable enough to get it round gradual corners. So that, as you're saying, Ben, means you can thread it through floor joists easily, relatively easily, once you've got the holes there big enough to get it through. If you take a 3-metre piece of steel duct, you find actually you've got a bit of a problem because you can't thread that in between the floor joists because it won't bend at all. So you might be pre-inserting some bits of rigid duct as you go so that you don't have to try and thread things in later.
And does some of this feed back into architects knowing what passive house is all about? For example, we're talking about floor joisting being the steel web that's going to incorporate ducting. You know, it gets to a point where the architects know all of this is coming, so that bit's covered, or do you have to advise back?
I think the architects know it's coming, but they don't know exactly what's going to go where. So it's good also to have a plan, a layout plan, just showing where you want to get things. It's actually interfacing with the structural engineer becomes an issue as well, because you might have a basic strategy of there's 250 millimetre thick floor with plenty of room to run your ducts, except for that full depth beam that goes across the middle of the open plan living area, which you can't get your ducts through, so you need to sort of coordinate with the structural plan as well.
When we get to the actual rooms, we've got a variety of different ways the air can come into the room. So Can you just describe a few of those and why they're different in different locations?
So we're looking to supply air into rooms in a way that you can't feel a draft. And if you've got a flat ceiling, the normal approach is simply the terminal is in the ceiling and it kind of has a disc that spreads air out horizontally so you don't feel the air blowing down on your head. The other sort of supply valve you've got is one that's designed to go in a wall, which will then just throw out air horizontally. In a domestic situation, the airflows are relatively small in ventilation or air conditioning terms, so it mixes up with the room air quite quickly. You don't really have to worry too much about the airflow and where it's going to go. So there's a air conditioning heritage of being quite concerned about, particularly with using cold air for air conditioning, whether it's going to suddenly drop really cold air on the back of someone's neck. But in a domestic situation with air going in at room temperature, it's relatively safe and easy to do without detailed analysis of the airflow sort of path.
How does this link in with moisture? Because that's one of the key benefits of living in a space that's got a mechanical ventilation system. You can get moisture out of the places where you don't want it anymore. So how do you build that into your calculations and your planning?
I'd go back a couple of steps and recognise the fact that when we live in a house, we generate moisture, water vapour in many ways. Partly we just breathe and perspire, moisture evaporates from us in that way, but that's only like about a fifth of what we put in. Then showering, you obviously release water vapour into the air from the hot water, but then you dry yourself on a towel and the bath mat. They sit there, they dry back out into the room as well. That's quite a big input of water vapour into the air. And cooking, boiling a pan of pasta, there's a significant amount of water vapour going into the air there. Also, when your dishwasher is drying off the plates or you've washed them up in the sink, again, water is evaporating there. And laundry, if you dry washing indoors, then you get water vapour evaporating from the clothes. And it's quite a lot. If you've got sake of argument, a 6 kilogram load of laundry, and it spins down to something that says it's 50% moisture content. That might be a 1200 RPM spin, I don't know. Depends on the type of fabric, but that basically means when it comes out, it's 50% moisture. So that's another 6 kilograms of moisture that's got to go somewhere. And where that goes is into the air in your house if you dry it inside. Obviously, ideally, you dry it outside, or you might have a condensation tumble dryer again, but still there'll be some moisture coming into the space. So all this adds up, and what it seems to add up to, roughly speaking, is about 2.5 litres of moisture per person per day. This obviously varies a lot depending on your lifestyle, laundry and bathing and cooking habits, but that's a rough number that we have in mind. So left to its own devices, we would get pretty soggy in our houses. So the way that moisture is taken out is through ventilation. Basically, at lower temperatures, you can get less water vapour in the air before it starts to condense. So even on a wet day today, if it's 10 degrees outside, the water vapour content of the air is relatively low in grams per metre cubed of air compared to the water vapour content in a humid house. So simply by bringing in outside air, at whatever condition it is, and exhausting the same volume of inside air, the inside air will have a higher water vapour content. That's how you get the water vapour out, basically. We can do theoretical sums and look at just how much air we might be moving through the building in order to do that. Again, assuming a normal average sort of water vapour generation per person.
So what assumptions are you using, or in your calculations? You've talked about people. Are they rules of thumb? How are you narrowing it down so that it does become more specific to the building?
Yeah, absolutely. When you look at any sort of domestic ventilation system, it's entirely on rules of thumb, basically, or regulations and guidelines. We don't do a particular calculation for someone's particular lifestyle habits. That would come about in a non-domestic situation. Possibly you'd look at things from first principles, but here we're looking at normal sort of occupancy, normal lifestyles, and that's been integrated into the Part F building regulations in terms of guidance of what sort of ventilation flow rate you want, based on a number of different sort of factors. One would be basically the number of people in the building. This is inferred from the number of bedrooms in the Part F. When we do a passive house calculation, we're more specific, and we do it on a per person basis. So we do that on a 30 metres cubed per hour per person, basically as a fresh air ventilation rate. And normally, pretty much everywhere, that will be the right amount of ventilation, give or take. We don't have to be super precise because the outside conditions are going to change a lot as well. So that just seems to be boiled down to more or less a rule of thumb that will work like that. Then you did mention about how we actually get the air out. So we do focus on the wet rooms. It's not actually that important to get too hung up on where we're extracting the air from in terms of moisture. Water vapour likes to get itself around the house quite quickly. So there has been a belief with intermittent extract fans in your bathroom that by sucking hard when you have a shower or a bath, that they will manage to pull all the water vapour out. There's a lot of houses in the UK with intermittent ventilation fans that are evidence that that doesn't work, and their humidity levels are rather high, and they're at some risk of getting condensation and mould in places. So what really works is running the ventilation all the time, and we do focus on extracting from the wetter areas, but it's the fact that the ventilation is always there that really makes our MVHR houses such a good humidity all year round, of not too high, not too low. There's kind of not much to be gained by turning the ventilation off at any point because you're not losing any heat through it. And if you need to shift a certain amount of air to get rid of moisture, then running the fans at a steady speed might be the more efficient way of doing it, rather than trying to get them to work really hard for a while and then back off. They might actually end up using more energy. So with this sort of approach where we're not losing heat as we do that ventilation, it does make sense to continue running it.
Just looking at the benefits, what would you say the key benefits are? We may well have mentioned some of them already, but the benefits of good ventilation.
Primarily it's to your health, I think. Through living in an enclosed space, we generate a number of pollutants. Some are a side effect of this moisture we're talking about. So at high moisture levels, very high moisture levels, you risk condensation and black mould, and that can be lethal in some cases. It's certainly not good for anybody. At lower levels, just a bit humid, we don't seem to mind and don't notice. But you'll also find that there are things like house dust mites that are also really happy in your bedroom and living away there, and they shed allergens, and people often suffer from allergic reactions, as in asthma, from that kind of thing. So getting the humidity lower, down to say about 50% relative humidity, makes life pretty intolerable for these beasties, but we're fine with it. So that's a real boon to your health in just getting it a bit drier, and then we have much lower problems with allergies in the house. Other areas, there's other things. It's the smelly stuff. There's all sorts of sources of smells. A lot of them are volatile organic compounds, and that also particularly applies to a category of things that kind of used to be associated with something called sick building syndrome. That came from carpets, vinyl flooring, possibly from your photocopier or laser printer as well. All sorts of, that's not the VOCs, that's other stuff, but there's all sorts of chemicals in the air that inevitably come out of the products used in the building or the processes going on in there, and just by ventilating we dilute them and remove them from the air. So that's all good.
Just before we move on from ventilation, is there anything else that's worth mentioning at this point as we think of mechanical services engineer, ventilation, passive house?
Yes, one of the snags that people have had with mechanical ventilation systems that haven't been designed with people taking this into account is the noise, actually. Noise from the fans. If you've got something whirring away at night, that can be annoying. You might find it difficult to sleep with. Also, in terms of tenants on low incomes, they can hear something whirring away and are conscious that must be using electricity, must be using their energy and their money. It might actually be quite a small amount, as we've seen, but in our design of passive house ventilation systems, we've got stringent targets on noise levels in rooms. This is going to be down to the sort of level where it's really not audible in the daytime, barely audible at night. Not everyone can hear it at all. So designing for low noise is important. Designing with suitably sized ductwork, as in on the larger side, reduces the noise input from the fans, but we still include silencers on both the supply ductwork and the extract ductwork from the MVHR, and that is kind of critical to getting a system that is easy to live with and therefore is allowed to do the job that it's supposed to do.
We started this whole conversation with ventilation for passive house, but what would happen if you were just doing this on a normal building? How do they account for ventilation?
Well, building regulations allows you to do either a really bad job or a not a bad job, and the bad job is kind of relying on the leakiness of the building to ventilate, which has never been proven to actually work. And because it was evidently not working in recent decades, we've now seen specifications required for even larger trickle vents than there used to be in windows to try and increase the leakiness of the building, and that means cold air drafts and higher heating bills. So people are inclined to close those vents anyway.
But it's basically a hole in the wall that's up to the user to open and close it. That's their solution.
Yes, with, as I said, there's those intermittent extract fans in the bathroom and kitchen, which you tend to be at liberty to use or not use. They tend to be noisy and irritating, and also they run for a short period of time. So they're effective when they're running, but when they're not running, they're not effective. So they don't really do that much. Then there's another approach, which is continuous mechanical extract ventilation, which actually has a lot to say in favour of it. It is a cheaper system to install. So here we just have either a central extract fan running, extracting air via ductwork, mainly from the wet rooms. It might include some other rooms as well. Then there's what's called a decentralised mechanical extract, which it looks like the normal intermittent fans really in the bathrooms and kitchens, and these are just designed to be quieter and run continuously. So that's the cheapest approach. Probable drawback is there's never any sort of thought about the total airflow through the building, and those little fans without any ductwork are just inevitably going to be a bit noisier and a bit more likely to be turned off. Going back to the central mechanical extract system with enough noise protection, that can maintain the same level of airflow through the building as a MVHR. So you can get the benefits in terms of removing the pollutants, removing the water vapour. Some systems are very carefully designed with intake. So you still need some intakes, air intake points, but these are much smaller than the trickle vent used for the previous approach, because it's all air's pulled through by the extract fan, so you don't need such big openings. And then some of them are controlled in relation to humidity in the building, so that seems to work all right. You don't have any there in the wet rooms. You don't want to be pulling air straight into the bathroom and out. You want to be pulling the fresh air into the bedroom. So with a humidity sensitive intake, it might open up when you're in there, adding moisture to the room, and then close down when you're not. And that seems to work reasonably well. Just relying on, particularly in a leakier building, you may not get the air coming through the bedroom where you'd like it to, so that doesn't always work as well as you'd like. In my experience, it doesn't really work as well as MVHR in terms of the freshness of the air that you feel and the nice environment in terms of not having stale smells, that kind of thing.
Let's move on to heating now, and where do we start with this one?
Okay, so all the houses we build will need some kind of heating system. Traditionally, heating engineers who do the installation have often been okay for putting in a gas boiler with radiators. That's very resilient type of system in that the boiler probably has much more capacity than you really need, but it can vary its output in response to the demand. And again, the radiators are quite powerful at high temperatures, so they can quite easily heat a reasonably well insulated house. The controls are quite straightforward. Again, you just have thermostatic radiator valves and the central controls on the boiler. So that system has not always needed that much oversight and thought if the heating engineer or installer is just sort of following the usual practice. Coming into this, both with passive house projects and moving on to heat pumps as the heat source, it's kind of needed to bring in a bit more thought to it. One of the aspects has been just looking at how you can trim the fat in the design with a passive house, because obviously we need much less heating. The other aspect is looking at heat pumps, where we've actually needed to give it a bit more thought in how you get a heating system that really works efficiently. Heat pumps are very good when they work well, when they're happy. There are cases where people have not had enough thought into the design of the heating system, so they might not have enough heating emitters, the radiators are too small, or maybe just one or two of the radiators are too small, but that's a problem because those rooms may not be warm enough. And then you have to run the heat pump at higher flow temperature, higher heating water temperature, and that really affects the efficiency badly on a heat pump, whereas it doesn't with a boiler. So we get into more detail of working out what size heating emitters you need in different rooms, making sure that everything's going to run. Again, heat pumps aren't able to vary their output so much up and down. So in the first place, you want to be more confident in what sort of heat load you've got, because you don't want to have a heat pump that's too small, but then you don't want to have one that's too big either. So knowing really what your heat load is a finer calculation than was needed with a combi boiler. So we do those to high level of accuracy. At least with a passive house as well, we know that it's going to be built to spec and it will perform as we expect, so that's good. And then we can also model what the heat output from the radiators will be at different water temperatures and that kind of thing, so we can have a system that really works as efficiently as it can.
And the ones that you design, are they wet systems, so you're still dealing with radiators and so forth?
Most of the systems we're doing are wet systems. It's not essential to do it that way, and part of it is cultural, I think. That's kind of what people expect. We've got a reasonably long heating season, not so long in a passive house, and we're expected to have fairly large quantities of water, hot water that is, and unlike a lot of other countries, most UK householders seem to want a bath, which is not easy to be done. You can't do that. You can do an electric shower, you can't do a bath instantly with hot water. So we're looking at hot water storage with heat pumps, and it's not entirely obvious to the rest of the world why we do it this way, but it's a Northern European thing, so I guess it fits the climate. So you find in New York, you would put in what you'd think of as an air conditioning system, really, where there is a heat pump, but it's more called an air conditioner, really, and that connects to units which are called fan coils, which blow air over the refrigerant heat exchanger, and they can either heat or cool the building. So they'll be heating in winter and cooling in summer, and the heat pump outside will switch modes, but still use the same equipment to do that. But in the UK, that's quite unusual. We've used a couple of those in small buildings where we could get away with a large open plan living space, and then this single point heater is quite a cheap and simple way to do it. Then you still need a separate hot water heater at that point.
And when we're talking about these wet systems, you often see most of the radiators downstairs. So is that just taking into account how airflow moves around and heat will rise, all that sort of thing?
Yeah, this does seem to take into account how heat moves through the building. Also the temperatures that people like to live with. People often want their bedrooms to be cooler, but their bedrooms are upstairs. But we still are ending up with heat distributed through the building. One of the things with a heat pump is that it's got a sort of minimum output where it needs to be able to get heat out. So it's actually quite beneficial to have heat emitters spread through the building so they can all take heat from the heat pump when it's running, because the compressor has got a sort of minimum speed that it can run at. And there's not really any point in trying to focus that into one or two rooms and then assume the heat will spread through the building. It will do, but there's just not much to be gained at that point. The other approach we've been using is underfloor heating. So this runs with a very low heating water temperature, so it is ideal for heat pumps in terms of running costs and efficiency. Now, traditionally, installation costs of underfloor heating have been quite high, so we don't always use that for that reason, although there are some ways of sort of integrating the underfloor heating into the ground floor slab, which can make it quite an economical solution, particularly if the controls aren't particularly complicated. That's where some of the money goes as well.
So you mentioned a little while ago about a hot water cylinder, that's often a good approach. So what considerations are there for hot water and cold water? Is this quite a simple one, or any tips for efficiency?
Yeah, there's a few things to think about here. One is, if you've got a hot water cylinder, to put it where you want your hot water to be used, because you're going to run pipes from that cylinder to the taps. I mean, you can't put it exactly where you want to use it, but if you've got a building with maybe a fairly central kitchen and the bathrooms might be off the landing as well, for instance, the main ones, then you want to look at, can you get the hot water cylinder towards the centre of the plan, maybe in a utility room, and not off to the far end of the east wing where the garage is, where the hot water is going to run down pipes all the way every time you open a tap.
I'm sure I've told you about my parents' place where I've timed it before and it's about 30 seconds to get some hot water.
Right, okay. That's how we like it in Britain. Yeah, so thinking about the location and trying to make it fairly central, because actually, again, it's something we come up with in Passive House. We take the heat load of the building down by about a factor of 10 compared to a normal building, and then suddenly your focus on everything else becomes relatively important. So there's a few ways of looking at the heat loss from the pipes, and the number one is put the tank near the pipes. That's going to fix most problems, and then you're probably going to get a fairly short run of hot water to the tap. Most systems these days use what's called unvented hot water cylinders. So these don't have a header tank in the loft. They connect directly to the mains. The pressure's limited, but the pressure is pretty high, so you can get a good shower off them. It also means you don't need such large pipes to run to the taps. So with a roof tank, a tank in the loft, you needed pipes of 22 millimetres or sometimes even bigger to run a bath tap with any enthusiasm. Now we can run everything in 15 millimetre pipes, just branching to everywhere, or another approach we're using, which needs a bit more calculation and thought, is a radial system with even smaller pipe work. 10 millimetre copper or 12 millimetre plastic will minimise the distribution losses on the hot water pipe work. What we avoid doing, although some people are quite enthusiastic about it, is running hot water in a continuous circulation loop around all the hot water taps. This is good from avoiding the time delay to get hot water at the tap, but the heat loss from keeping that circulation loop hot all the time is inevitably quite a lot, even with the best insulation that you can practically apply. So that's best avoided in any case, and certainly best avoided in a passive house where a lot of the year you're not going to need any heating, and that's going to be heat you don't actually want in the building.
Have we mentioned all the key areas that you, as a mechanical services engineer for Passive House, would overlook, oversee and build into your designs? Are those the key?
Those are the key areas, yes. Yeah.
Okay, what are you handing over then? If someone comes and hires you, I want you to do this job, what are they wanting at the end of this?
I suppose they're wanting a heating and ventilation system that works well and efficiently and doesn't cost too much to install.
So a spec of the actual system.
Yeah, so in practical
and plans,
terms,
yeah.
Yeah, it depends a bit on how much other suppliers and so on are installing the system. So at the starting level, you want a sort of overall strategy and specification that is going to make sure that the place does meet the ventilation requirements, and it meets the ventilation requirements of the passive house as well for a passive house job, and that you will get the heating and hot water that you need, but not get more complication and expense that you don't need. So we have, some people might not really believe they need any heating, but we can look at the energy model and see that, well, that it's designed to need some heating, but not much. So how do we deliver that economically? So in terms of what we might deliver then would be specifications. On the ventilation, it would certainly start with the flow rates, and then it could include ductwork sizing and so on, or that could go to a specialist supplier who does detailed design and supply of the equipment. On the heating side, again, one of the things with the introduction of heat pumps is a bit more focus on the training and rigour of heating system design. So we are seeing heating engineers starting to take this on in more detail as well. But we could ourselves do the design of the heat emitter systems or the underfloor heating or something like that, and all the pipe work and so on. And also being confident in what size heating system you need in terms of heat pump size, hot water cylinder and so on, and being able to specify that so you can get prices on what you want.
And in terms of technical drawings, are there names for all these drawings that would then be passed on?
There's a couple of names, I guess. I mean, we generally, what the architects might call as a general arrangement would be used as a background for a layout plan. Do you just want to lay out exactly, show on a two-dimensional plan where things are? Ductwork designers might prefer to work in a three-dimensional model because they've got quite significant spatial requirements. They might still boil that down to two-dimensional plans for ease of seeing on site what you're doing. So that's the layout drawings. Might include sections, details of the plant installation, for instance, where the MVHR goes. You might want to know the dimensions of where the holes go through the wall. You might want to know how high the unit is off the floor and all that kind of thing for internal planning. Similarly with the pipework and the radiators, you'd have both sort of layout plans just to show where things go physically in the building. The other side of that is you might have a schematic drawing which doesn't relate sort of as a scale drawing. Instead, this is a diagram of how things connect together, so you've got much more room to spread out where the control valves go and so on, and you don't really worry about all the radiators and that kind of stuff. You just focus on exactly how you've connected together the heat pump, where you might have a filter in the system, a diverter valve, and the hot water tank and all that kind of thing. So that's what's called a schematic drawing. You also get those for wiring. Again, you don't draw scale drawings of wiring, you just want to know what wire connects to what terminal. That's the key thing there.
Are you working in a specific program, or does each thing need something different?
Personally, I work in Excel as a calculation method, really. This is where PHPP is based, so it comes from that. I know there's other bespoke software, things like Heat Engineer make software for heat load calculation and heating system design. If you're doing building regulations calculations, then you need to use SAP software, but that's a separate division from passive house design. But not much else really, I don't think. And then drawings just could be any CAD package. It could be some people work in a three-dimensional one or a two-dimensional one. That doesn't particularly matter. It's just whatever sort of drawing package either suits you or integrates with other members of the design team.
What does your day look like? What tasks might you be doing if we just said, this is a typical day with Alan, or this one here?
I think instead I'll probably just try and talk about how we might spend our time on these particular jobs we do. The reason for that is that's now not all I do. So I've spent most of the last couple of weeks working on teaching and training materials and so on. But in terms of this sort of design process that you've got, it will involve a review of architects' designs, maybe a chat or emails about exactly what their brief is and what their requirements are. These days it will probably be a Zoom video call with clients, again, to just understand how they might be living in their house, what sort of things they've got in mind in particular. So then we'll be getting into drawings and, say, at the first stage, possibly pre-planning, or when the planning drawings are just sort of there as a base, looking at where you're going to put key bits of ventilation and hot water kit, and if you've got a heat pump, where does that go outside? That is really easy on a rural site with ground all around. It can be quite tricky in a infill plot in an urban area, so you need to think about what the constraints are there. So then when you get that sketched out, you'd like to be able to sort of draw a line under the strategy, and then at this stage the architect's probably detailing up their plans going to stage 4 construction information, and hopefully going with as much as is complete information as possible, but in time to still get it integrated. You want to look at laying out the building services distribution really, and emitters and ventilation terminals and all the key bits of plant on the layout drawings. And you'll also be drawing up a specification, which will both be the shopping list for the contractors for what equipment you want, and specify the particular requirements of the installation and the workmanship, commissioning and that kind of thing.
Are there any reasons that things might be revised? So you send across plans, what might change?
all sorts of things change. There's when people are designing houses as a client for the first time, they don't quite necessarily know what they're getting, and as it evolves, they think more about what they really wanted, and so that ideally happens still at the drawing stage, because I think interpreting drawings into a three-dimensional finished building is an acquired skill. So sometimes you also get people coming into the building site as the walls go up. They might be thinking, "Oh, I don't want to do that like that," and start to change things. So that's, from a designer's point of view, is maybe a bit of a hassle, but it can make sense for the owner of the house, though. So that can be sort of a bit of extra work, but it can be worthwhile.
What makes a good mechanical services engineer versus one that you really don't want anywhere near your project?
I think it's got to be someone who listens and understands what you actually want. You could come in with a preconceived idea of a fantastically complicated, technically awesome bit of automated building control, so that, I don't know, the lights all respond to the time of day, they change their colour temperature as the sun moves around the sky, and they respond to your voice and all sorts of things. But if the client wanted a light switch and a bulb, that wasn't necessary. It's a waste of time and a waste of money. So you've got to understand what your brief is, and you want to have some experience in the field and be able to look back at other projects and be sure of what has worked well. And even though we're doing what seems to be quite innovative buildings, actually we're looking around one this morning and the ventilation system's all humming away absolutely fine. It's been pretty straightforward to design and install because we've done it before. The first time involved a lot of head scratching, but now it's fairly straightforward, and I don't see any problems with that.
Does that make life easier if you're almost part of a team of people who've worked before together and you know a lot about how each other works? Absolutely, yes. So there's, on the one hand, there's architects who've spent time working together, and particularly where they've been working on, for instance, passive house buildings for a while. They may still not be numbers types people who aren't really going to get into the passive house design spreadsheet and that kind of thing, but they still, after a bit of feedback from both of us, we kind of know what each other wants in terms of the building design, and that makes things a lot easier. Can be the worst where the architect thinks they know what you want and insist on trying to design it when it's not what you want in terms of, for instance, services space and that kind of thing. Or they have decided that you really must have a roof pitched this way because that will be optimum for solar collection, but that is really making life hard for a lot of other things and turns out not to be that important for the solar energy either. Well, finally, is there anything else we haven't mentioned, or a closing thought, something that would be good in this topic about what this particular role entails, who it helps, what goes on? I suppose overall this is it can be seen as a bit of an optional role, and maybe it should be. Say there's things like a structural engineer has to follow certain codes, and in this country certainly architects don't have the training and ability to deliver what's necessary for the building regulations and for the safety of the building. Areas of the heating and ventilation design can be split off into separate packages as a sort of design and build by various different subcontractors. I mean, that can appear to have benefits in terms of avoiding having someone else on the design team. Obviously the downside is that they're probably not talking to each other as separate entities, and you don't get such an integrated design. And particularly when we're talking about specialist houses such as passive houses, they're not familiar with how they respond and what sort of level of heating, for instance, you're really going to need. So in that case then, what would you say the core benefits of investing this money in this consultancy are? They would be in basically getting a single point of contact to brief what the system would be and discuss what you need, and also then getting one person to oversee how systems work together
and keep a track on how it all gets commissioned and is all seemed to be working at the end as well.
Well, Alan, really appreciate both the information and your time. Thank you very much.
All right, nice to see you again, Ben.
Get more in our show notes today, which you can find at houseplanninghelp.com/331. We always provide a summary for you so you can whiz through the information once again and dig out the bits that you're interested in. Perhaps you have a comment or you'd like to ask a question. Well, you can discuss it with us on social media. We'll give you the links, or within the show notes, just scroll down to the bottom there. We also talked about Facing Future and that special episode on housing that they did. We'll put that at the bottom of the show notes as well. So all of that at houseplanninghelp.com/331. Well, if you enjoyed the podcast today, remember there are plenty more in the archive stretching back over a decade. But the other thing that we do is run the Hub, and this is the membership community that I try to spend as much time in as I can, particularly chatting with you about your projects. We have an office hour where you can check in with me. We have other calls as well where you can bring up your projects. In fact, I might as well mention one that we've just done a live training with Guy Hargreaves, who is the homeowner of the Kimver project that we have featured extensively. It was one of our in-depth video case studies, and I thought this could be a really good way to round things off. If anyone has any questions, we get Guy on, and Guy's brilliant. He's shared so much information, the good, the bad, and so forth. So he was really good. And what was interesting on this call, we also had Jason, who is pretty much about to embark on the identical project, Victorian terrace house, mid-terrace, same issues. So we wish him luck, and hopefully you two chatting together will help you, Jason, on your journey. We've got the courses, we've got the forum, all of that. Take a look, houseplanninghelp.com/join. That's it for today. Thank you so much. The House Planning Help podcast is produced by Regen Media. Content that matters.